Hey guys, so this is part 3 of chapter 10, and as promised, we're starting off with hybridization. We talked about the concept of overlapping atomic orbitals in the last video. Now, that concept of atomic orbital overlap applies equally well to polyatomic molecules, not just a diatomic molecule like HH or HF. So first, let's really define what hybridization means. It's the mixing of two more atomic orbitals to form a new set of hybrid orbitals. And usually that mixing of atomic orbitals happens to the central atom. Now, when you mix at least two non-equivalent atomic orbitals, for example an S and a P, those hybrid orbitals will have completely different shapes from their original shapes. Remember that their S is a sphere, P orbitals were a dumbbell shape. So now when you actually make these hybrid orbitals, they don't look exactly the way that they started. Number two, the number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process. What that means is that if you start out with an S orbital and a P orbital, that's all you're going to have when you make these hybrid orbitals. In other words, you can't make up new orbitals because you're mixing two original orbitals together. As an example, if I have something that is an S and a P, my hybrid orbital cannot be SP and a D orbital. That just doesn't make sense. So whatever you start with is what you end up with. And number three, covalent bonds are formed by overlap of hybrid orbitals with atomic orbitals. And by overlap, I mean just basically a sharing of common space. And then also the overlap of hybrid orbitals can be also done with other hybrid orbitals, but that's a little bit more complex. We're not going to worry so much about those this semester. Okay, so here as an example, let's consider the CH4 molecule, okay? And here we're only going to focus on the valence electrons of carbon. From previous knowledge, we know that CH4 is going to have a tetrahedral arrangement because that central atom has no lone pairs and it has 4 bonding pairs. But if we focus on those valence electrons of carbon, we notice that carbon only has 2 unpaired electrons, one in each of the 2 p orbitals. And with that knowledge, we should assume that it would only bond 2 times with hydrogen in its ground state. So how do we account, if there's only 2 unpaired electrons, how do we account for the 4 bonds that carbon makes in CH4? And that's the conundrum that prompted these new theories, the valence bond theory and the molecular orbital theory, because the whole point is to make a full octet. But right here you see that the valence shell of carbon only has 2 unpaired electrons. So how does that happen? Well, the valence bond theory says that there is a hybridization of atomic orbitals happening here. So what that means is, what if I was to promote one of those electrons in that S orbital up to the P orbital? And of course, this only happens with an input of energy. So if we do that, and here I'm showing you how the electron orbitals originally look. Remember, the S is a sphere, the P is a dumbbell shape. But now if we promote that S electron to a P orbital, we have this thing called hybridization. We're mixing 2 orbitals together. And now what that shows you is that not only is there a shift in how the orbitals look, you can tell from the hybridization orbitals, they don't exactly look like dumbbells, they're a little bit different, but now you have 4 unpaired electrons, which accounts for the 4 bonds that carbon makes in a CH4 molecule. So this is the basic technique that happens when you do hybridization of atomic orbitals. And this concept can be applied to every molecule we have. So here I'm showing you an sp3 hybridization because you're using 1 s orbital and 3 p orbitals. I'm going to show you examples of an sp hybridization and an sp2 hybridization, but it's the same concept. And that's all you're going to be responsible for. It's just an sp3, sp2, and sp hybridization. You'll notice that your book has more complex ones that involve the d orbital, but that you're not going to be responsible for in this semester. So here we have the formation of an sp orbital. Okay, so as an example, I give you beryllium dichloride. As you know, the valence electrons of beryllium, which is the central atom, has a electron configuration of 2s2. It's of course 1s2, 2s2, the full thing, but the valence is just 2s2. Looking at that, then beryllium shouldn't really bond with anything because it's paired up, but it does. So how do we explain that? We explain that by a hybridization of orbitals. So if I would now promote promote one of those electrons to a p orbital, you would have 2 unpaired electrons, which accounts for the 2 bonds that beryllium makes. So everything is exactly the same. It's just now, instead of being sp3, because the other one, CH4, had 1 s, 3 p orbitals, this one only has an s and a p. So this is called an sp hybridization. In the same manner, you have something that we call the sp2. This would involve 1 s orbital and 2 p orbitals. An example of this would be boron trifluoride. The electron configuration of ground state boron would be 1s2, 2s2, 2p1. It only has 1 unpaired electron. It doesn't make sense. So for it to make sense, we have to use this hybridization technique and promote one of those s electrons to a p orbital. And now that gives it 3 unpaired electrons, which accounts for the 3 bonds that boron makes. As an example, let's try this problem. Determine the hybridization state of the central atom in the following molecule, SiBr4. They will want you to describe the hybridization process and determine the molecular geometry. So the ground state electron configuration of silicon is neon in brackets 3s2, 3p2. We're only going to consider the valence electrons of silicon, and we notice that it's 3s2, 3p2. That doesn't account for the 4 bonds that silicon makes. So what we're going to do is we're going to promote an electron to a p from an s orbital to a p orbital, making it a sp3 hybridization, and that accounts for the 4 bonds that silicon makes. The molecular geometry is just like CH4, so it's a tetrahedral geometry. Since there are no lone pairs on silicon, the molecular geometry is also the electron pair geometry. Pretty simple. Let's move on. So this concept of hybridization is useful for all types of molecules, even those that involve double and triple bonds. Consider the ethylene molecule, C2H4, which I'm showing you a molecular structure here. If you did the chapter problems, you notice that 10.1 involved this same molecule, C2H4. And as you can see, it contains a carbon-carbon double bond and has a planar geometry. The geometry and the bonding can be understood if we assume that each carbon atom is sp2 hybridized. So here, I'm showing you the ground state electron configuration of either of the carbons. It would be 2s2, 2p2, and we know that carbon is making 4 bonds, so this kind of doesn't make sense. So what we do is we go ahead and we promote the electron like we've talked about before. But here we assume that only the 2px and 2py orbitals combine with the 2s orbital, and that there is one left untouched, the 2pz. Remember, p orbitals is px, py, pz, right? So here we're saying that since each carbon is sp2 hybridized, there has to be a p orbital that's left over, and that would be the 2pz orbital. This figure shows you that the 2pz orbital is actually perpendicular to the plane of the hybrid orbitals. So now you're probably asking, how do we account for the bonding, right? How does this really happen? How do we account for the bonding of the carbon atoms? And that I'm going to show you right here. This is figure 10.16, and it shows that each carbon uses 3 sp2 hybrid orbitals. Okay, so right here, forget about the double bond right now. Just know that carbon is bonding to 2 hydrogens and to 1 carbon. That's 3 bonds. So that would be the sp2 portion, the hybrid portion. So we have that other p orbital, the pz orbital. So how does that bond? That basically takes care of the double bond in C2H4. So when we talk about hybridization in molecules that contain double and triple bonds, we make a distinction between the 2 types of covalent bonds. There's 3 bonds that are formed by each carbon, the hybridized ones, right? So and those are called sigma bonds. In other words, the definition of a sigma bond is covalent bonds formed by orbitals overlapping end to end. The picture shows that the orbitals are coming together, overlapping end to end, okay, in this picture. The second type, PZ, the one that was left unhybridized, it would be considered a pi bond. So you have sigma bonds and pi bonds. The pi bond is defined as a covalent bond formed by sideways overlapping orbitals with the electron density above and below the plane of the nuclei of the 2 atoms. And you notice that the PZ orbitals are on top and below those 2 carbon atoms. It's this pi bond, the PZ, it's this unhybridized p orbital that forms the pi bond that gives ethylene the planar geometry. You can see the orientation of the sigma and the pi bonds here. And even though we normally represent the carbon-carbon double bond as a normal Lewis structure with, a C, two lines, and another C, we got to keep in mind that those two bonds are two different types of bonds. One's a sigma bond and the other one's a pi bond. And this bottom picture shows you that all of the bonds putting together. So you see that there's 3 sigma bonds in the carbon. Those are the ones that are connected end to end. And then you've got that other bond, the pi bonds, which create the actual double bond in C2H4. So there's a difference. You have to make that distinction. Even though in the Lewis structure, like I said before, we just draw them as 2 lines, those 2 lines connected to those carbons are not exactly the same. One's a sigma, one's a pi bond. And here is just a little summary, right? So a single bond is comprised of 1 sigma bond. A double bond has a sigma bond and a pi bond, just like I explained to you. What about triple bonds, right? So acetylene, for example, would be C2H2. If we were to do the Lewis structure, you'll see that that has a triple bond, and that is made up of 1 sigma bond and then 2 pi bonds. All right, so there's 2 lines that are above and below the nuclei of those 2 bonding atoms. Okay, and here I'm just showing you another view of the pi bonding in the first example, C2H4. And you see that the electron density map shows that there's a huge electron density above and below that double bond. And that, of course, is because of the pi bonding that's going on. So, like I said, what about triple bonds? And here I'm showing you the sp hybridization of carbon in acetylene, which is C2H2. Here, the hybridization of carbon would be sp, because the 2s orbital is mixed with only 1 2p orbital. And then you have 2 remaining p orbitals that are unchanged. They're unhybridized, right? So that's when you promote the electron, right? And then you only take, here I'm showing you the sp. So there's an sp hybridization that's going on between a carbon and a hydrogen. And then you've got these 2 unhybridized orbitals. So those 2 that are unhybridized are what going to make the 2 extra bonds, to make 3 bonds in total, which is a triple bond of the C2H2 molecule. So here's what C2 acetylene looks like, right? It's C2H2, and you've got these sigma bonds, right? So you've got a sigma bond being made between the hydrogen and the carbon, and then another sigma bond being made between the carbon and the carbon. So that only takes care of 2 bonds, but you've got to account for the other 2 bonds that carbon needs to make to equal a total of 4. So that's what the 2pz takes care of. And then you have another one. You have the 2py that also is unhybridized, and that is also shown right here. It kind of looks like a hot dog, right? But here's what you would see for the entire molecule. Again, you've got 2 sigma bonds being made, one between the carbon and the hydrogen, and the other one between the carbon and the carbon. And then you've got 2 separate pi bonds being made, each between the carbon and the carbon. That, of course, totals 4 bonds for each of the carbons. And then here, I'm just showing you another view of the bonding in acetylene, and you can see that the electron density is greatest between those 2 carbon atoms. Okay, let's do a quick example. This is 10.5 in your book. Describe the bonding in the formaldehyde molecule whose Lewis structure is this. They want you to assume that the oxygen atom is sp2 hybridized. So if we follow the same procedure that I just explained, you can solve it this way. So there's 3 pairs of electrons around the carbon atom. That means that that carbon atom has to have a trigonal planar geometry. Recall the shapes back in when we were talking about the Vesper model. The first thing we got to do is figure out what hybridization the carbon atom has. And if we do the same thing that we did before, the valence electrons of carbon, ground state, is shown here. But if we promote one of those electrons, you're going to have then an sp3 hybridization. But there's a double bond here. So that means that really that carbon atom is going to be an sp2 hybrid. And you're going to have a leftover unhybridized orbital, which is that 2pz. And that 2pz is going to be the pi bond. That's the one that's going to make that extra bond between the carbon and the oxygen. So basically, carbon has 1 electron in each of the sp2 orbitals, and those are used to form the sigma bond. So you've got 3 sigma bonds being made between carbon-carbon, carbon-hydrogen, and carbon-hydrogen. And then you've got that extra bond, which is a pi bond, and that's being made between the carbon and the carbon. And you can see where the electron density would lie. It would lie mostly between the carbon and the carbon because of that extra bond. Okay, so that's all for this video. I would like to point out that there is an animation that I have placed on Blackboard that kind of goes over this hybridization of molecules with triple bonds and single bonds and all that, so it might be beneficial for you to see that. And next video we're going to talk about molecular orbital theory. All right, so I would suggest that you practice this. This will be on your final, but keep practicing because these are really, really important. All right, guys, see you later.